As another example, let's consider the same region, and we want to find the moment of inertia about the y-axis. Now, moment of inertia is defined as the sum of mr squared, where r is the mass, and m is the mass, and r is our distance from the axis of rotation. In this case, the axis of rotation is the y-axis. First, let's just do a representative sketch of our region. Our region, as before, runs from x equals 0 to x equals 1, and the curve bounding the region from above is y equals 2 minus x squared. Our density function is still going to be 1 over the square root of 1 plus x plus y squared, giving us an integral we might not even be able to evaluate, but let's go ahead and write it down. Now, the process is simply the same as before, and the process is always the same. We consider an interval of one of our axes, and we let this be the ith interval. We consider what the region above that interval contributes to our moment of inertia. Now, I considered an interval of the x-axis because for our sample point xi star, xi star being our sample point, xi star is at a constant distance from the y-axis, so that our r in the calculation of moment of inertia is just going to be xi star. Now, we're going to consider partitioning with respect to y, taking a limit as delta y approaches 0 so that we get an integral for this strip, then summing over all x intervals, obtaining a double integral. This leads us to a typical interval, or typical region, where we're going to have a y sub I star, sample point, and an x sub I star. So we have, in the typical region, sample point xi star, yj star, and that's yj, not yi. Sample point will be somewhere in this region, and if we enlarge our region, we see that it's of dimensions delta x by delta y, with the sample point somewhere xi star, yj star. The distance of our sample point from the y-axis is xi star, and this is our typical area increment delta A sub ij. The area increment corresponding to our x increment, our ith x subinterval, and our jth y subinterval. The mass of this integral, of this interval, is delta m sub I j, which is equal to the area of the interval multiplied by the density. and we'll say density sub ij. The area is just delta x times delta y. Multiplied by the density ij, which is just the density at the point, sample point, x sub I star, y sub j star. So we have a representation of the approximate mass corresponding to this rectangular subregion of our plane region defined by this graph. We think in terms of adding up the areas of all these intervals, all these subregions, and of adding up the masses of all the subregions. For every x interval, we have a subdivision along the y direction that runs from the x-axis up to y equals 2 minus x squared, with the x evaluated at x sub I star. And then we sum that over all other intervals, subintervals of the x interval. The picture that we get could be represented generally and with no attempt to be very neat about it. We subdivide our x interval. For every x interval, we subdivide our y interval. Our y interval runs from 0 to f of x, whatever the function is. Having subdivided one vertical strip, we then sum over all the x intervals, doing the same thing to every one of these strips. And I'm not going to draw all these lines, but you understand that I'm subdividing each strip so that I get a large number of small intervals, all contributing a mass, delta m sub ij, where I is the index of the x interval, j the index of the y interval. Now, it's not mass that we're trying to find, it's moment of inertia. So how do we get the moment of inertia? Well, the moment of inertia is mass times r squared. R is our distance from the axis is the y-axis, so as we've seen, r is simply distance from the y-axis to the strip that we're talking about, and that distance is going to be represented by the sample value x sub I star, so that the contribution of our ij interval to the moment of inertia is going to be written as delta capital I indexed by small I and j, capital I having nothing to do with small I, and that's going to be delta m ij times xi star, and we're running out of room here. This is that quantity squared. Going to have to move this paper over a little further to have room to write here. So that our total moment of inertia, which I can write as I total, is the sum from I equals 1 to n of the sum from j equals 1 to m of our delta m ij times xi star squared. And this is an approximation. We're going to take the limit of this expression as our delta x's and our delta y's, and it looks like, excuse me, I've left off the delta y and the delta x here. Okay, well, we're going to write this on a separate sheet of paper and analyze this approximation and take the limit as our delta y and delta x approach 0.